Hello, in this video we are going to introduce a method for classifying the states in a Markov chain. As such, by the end of this video you should thus be able to determine whether the states in a Markov chain are transient or recurrent, and you should be able to use this classification to describe the limiting behavior of the chain. Let's begin this process by briefly reviewing what we have learned thus far about Markov chains. Here I have a description of a game of catch played between four players. This process is clearly Markovian, as the probability each player has the ball on the next turn depends only on the person holding the ball at the present time. In other words, when Dawn receives the ball, she does not think about who threw it to her when she decides who to throw it to next. What I would like you to do now is to pause the video and use what you have learned to draw out a transition graph for this Markov chain. You should have drawn something like this. Now write out the transition matrix. Incidentally, notice that we have assumed here that for a player like Dawn, who can do one of three throws, the probabilities of each of these are equal to 1/3. Let's suppose we now actually watch a game of catch between these people. Here they are, and here is the ball that we have initially given to Dawn. The game might proceed as follows. Dawn first throws the ball to herself, she then throws it to Carlos, Carlos throws it to Conrad, Conrad throws it to himself, he throws it to Dawn, and Dawn throws it to Stephen, who then continuously throws it to himself. The point of this example is that the ball is eventually passed to Stephen, who does not throw it to any of the other players. Stephen, in this game, does not play well with others, and just throws the ball to himself. We can thus predict that whenever this game is played, the ball will eventually be held by Stephen. This may take different amounts of time, but it is an inevitable consequence of the rules of the game. We call these sort of inevitable consequences, in this case the fact that the ball is guaranteed to end up with Stephen, the limiting behavior of the Markov chain. And we introduce a classification of the states in a Markov chain that would in this case place Stephen in a different class to his fellow players. Hopefully it is clear that Stephen is placed in a different class and is a different type of state to the others because he refuses to pass the ball to anyone other than himself. To understand this classification of states a little better, it is perhaps worth considering a few other example Markov chains. As a first example, consider the following rules for a game of catch, a Markov chain. If you need to, pause the video and take a moment to draw out the transition graph. The question is, which of these players are more like Stephen and which are more like the other three players in our previous example? The answer, I hope you will agree, is that players 1 and 5 are like Stephen, as both of them refuse to pass the ball to anyone but themselves. If we wait a sufficiently large amount of time and examining the limiting behavior of the chain, the ball is thus guaranteed to end up with either player 1 or player 5, just as in our previous example, where the limiting behavior was to end up with Stephen. Let's now turn to a second different example. Here I have drawn the transition graph directly, and my question once again is which players are like Stephen. The answer here is players 1 and 5, although perhaps the question should have been asked the other way round. That is to say, perhaps we should have asked which players were like Dawn, Carlos and Conrad. If you remember our first example, once the ball was passed to Stephen, Dawn, Carlos and Conrad never once touched the ball again. This is like what happens to players 2, 3 and 4 in this game once the ball is passed to player 1. Players 1 and 5 toss the ball between each other and never pass it back to players 2, 3 and 4. They essentially ignore these players and choose to play their game on their own without involving 2, 3 and 4. Let's now move on to this three-player final example in which everyone can throw the ball to everyone else and ask the question, is what we observe for the players of this game more like what we observe for Stephen or more like what we observe for Dawn? I hope you will agree that the limiting behaviour observed for these players is more like the behaviour that we observe for Stephen. If you remember, as we went to the long time limit in our first game, the ball was always passed to Stephen, who refused to pass it to anyone other than himself. As a consequence of this, the limiting behaviour in that system was for the ball to end up with Stephen. As the game progressed, the probability that Dawn would be holding the ball tended to 0. Now in this game, everyone passes to everyone else, and thus no player's probability of holding the ball goes to 0 as the game progresses. So in this sense at least, the players here are more like Stephen, who has a finite probability of holding the ball when the number of throws in the game goes to infinity. When the number of throws in the game goes to infinity, the probability that Dawn will be holding the ball in our original game goes to 0. We state that the states in a Markov chain that are like Stephen are recurrent, and that states in a Markov chain that are like Dawn are transient. Furthermore, to make these distinctions precise, we introduce the following definitions of transient and recurrent states. In doing so, we introduce a random variable known as the return time or recurrence time to state J. This return time measures the length of paths that start in state J and that finish in state J. This is clearly a random variable. To be totally clear on what this return time measures, let's consider how the Markov chain plays out with a particular set of goes. Let's suppose that we start in state 1 and thus measure the random variable R1, the return time or recurrence time for state 1. The state we will move to on the next step of the chain is clearly random. For illustrative purposes, let's say it's state 3. We now know that this particular instance of the return time, R1, will be guaranteed to be greater than 1 as we have had one step of the chain and have not yet returned to state 1. Let's now suppose that in the next step we move from state 3 to state 3 again. We are still not back to state 1, so the instance of the return time will be greater than 2. Next, we move from state 3 to state 2. As we are still not back in state 1, though, we have still not generated an instance of this return time random variable R1. All we know is that for this particular generation, R1 must be greater than 3. Let's now have the system return to state 1. We thus have a set of 4 steps that started and finished in state 1 and have thus finally generated an instance of the return time to state 1 random variable. In this case, it is 4. It is important to note, though, that r equals 4 in this case because of the path we took around the states of the Markov chain, which was random. If we had gone round a different path, for example, if we had gone to state 2 and back to state 1 again, we would have gotten a completely different value for the random variable R1, in this case 2. What is guaranteed with this chain, however, is that R1 will always be less than or plus infinity. It is possible to get from every state to every other state in this chain, and hence whenever we leave state 1, we are guaranteed to return to state 1 at some point in the future. We can thus confidently assert that all the states in this chain are recurrent, as the probability that the return time to state 1 is less than plus infinity is equal to 1. Whenever you leave a state, you are guaranteed to return to it at some point in the future. Contrast this situation with the situation we find for one of the other transition graphs that we introduced in this video. Let's suppose that we start in state 4 of this chain and begin throwing the ball around. It might initially move between players 4, 3 and 2 as shown here. It will eventually, however, be thrown to player 1, and players 1 and 5 will never throw the ball back to players 2, 3 and 4. It does not matter how long we wait, the ball will never ever be thrown back to players 2, 3 and 4. The consequence of this is that there is a finite probability that the return time to these three states, states 2, 3 and 4, is equal to infinity. Once the ball is thrown from player 2 to player 1, even if we wait an infinite amount of time, the ball will never be thrown back to state 2. By the definitions above, states 2, 3 and 4 are thus transient, while states 1 and 5 are recurrent. To summarise then, we have introduced a classification of the states in a Markov chain in terms of the chain's limiting behaviour. We have stated that if, when we leave a state, there is a finite probability that we will never return, the state is transient. If, however, on leaving the state, it is guaranteed that we will return in the future, then the state is recurrent. As an exercise, try to go through this video again and classify the states in each of the chains shown as transient or recurrent. Answers are available in the comments section below, so you can test if you're right or wrong. Thank you.